Let's look at this example and talk about how some examples are totally fine to do either way. This problem, I want to find the dimensions of the open rectangular box with a volume of 32 cubic feet. That's the minimum surface area. I can totally do this either way. So the usual way that we've been doing things, I want to minimize the surface area, which is going to be the base x times y plus the front and the back sides, which are both x times z, plus the left and the right sides, which are both y times z. So there's the thing I'm trying to minimize. And in this particular problem, my constraint, I may have said something that's actually not true. That's totally fine. My constraint here is going to be that, what have I got here? I want the volume, which is x times y times z, to be 32. We can probably do this one both ways. I'm just, yeah. I don't spend a lot of time thinking about LaGrange multipliers, but I should. So here, we could do this by isolating one of the variables here. It doesn't really matter which one we pick because it's fairly symmetric in our variables. I would probably isolate z if there was no reason to pick something else. So if we solve or isolate z, we're going to get z equal to 32 divided by x times y. And if we stub that back into the equation here, my surface area equation is going to equal x times y plus 2 times x times 32 over x times y plus 2 times y times 32 over x times y. Yeah, do I not have, oh, wait, I guess I'm not sure where you mean.
And the surface area equation?
No, it's only one x, y, it's an open top box. Yeah, good call. So notably, if we look at this here, I'm going to simplify before I start taking partial derivatives. My surface area is going to be x times y, and cancel x here, I get 64 over y, or 64 times y to the negative first. Same deal here, y's cancel, I get 64 over x, or 64 times x to the negative first. I'm going to point out, as I often point out, that this particular equation happens to be symmetric in the variable x and y, meaning if you interchange x and y, you would have the same equation. That typically leads to x and y equaling the same value. Not always 100% of the time, but most of the time when we see the same. So we take our partials. I should have called this f. Let's call this f of x, y. Then fx is going to be 1 plus 0 minus 64 x to the negative second. So that equal to 0, and fy is going to be the same sort of thing. 1, sorry, not 1. Whoa. Fx here shouldn't be 1. What should it be? Sorry, if I go back, I'm taking the derivative of x, y. I should get 1 times y. Yeah. Woo. And here, when I take the partial with respect to y, I should get 1 times x. And then I'm going to get minus 64 y to the negative second. This is maybe a mild pain in the butt to solve, but it's not too bad. If we isolate y and write it as y equal to 64 divided by x squared, then I can substitute that back in for y over here. So I'm going to get this. So this is going to become x minus 64 over y squared equal to 0. I'm going to plug that in down there. So I'm going to have, it's going to look gross for a second, x minus 64 over 64 over x squared equal to 0. Okay, but I should definitely make this a little bit nicer. It's going to be x minus 64. And instead of dividing by 64 over x squared, I should multiply by x squared over 64 squared. Cancel 64. Then I've got x minus x to the 4th over 64 equal to 0. Factor out an x. So I want x cubed equal to 64, which gives me x equal to 4. Or x equal to 0, but we know that's not a good answer because it doesn't make sense for the shape to have a base of 0. And then we go back and we plug it in, we find y, we get y equal to 64 over 4 squared, which is going to be also 4. And finally, we go back and we solve for z, and we get z equals to 32 over 4 times 4, which is 32 over 16, which is 2. You might observe here, I didn't go and find that this was actually a minimum because I'm lazy. But really because you will see this happen a lot, where if they're asking you to find the thing that minimizes something, it's gonna, and you only find one critical point, it's gonna be the thing you want. We totally could, right? We could find the second partials. It's not too terrible to do. I guess I could write it up here. We could say, yeah, FYY is 1. Oh, sorry, that's not true. That's a lie, and you can't see it. Good, it's a lie. FXX is going to be gross. It's going to be positive 128 over x cubed. FYY is going to be the same, 128 over y cubed, and FXY is going to be 1. So if you throw that all into your gamma is going to be this times this minus 1, and you plug in your 4, it should work out to be positive and then concave up, so it's a minimum. I know you know how to do that, so let's move on. Let's move on to seeing how this probably would have sucked less if we'd used LaGrange multipliers. So a lot of the time, it's not that you, so I should say, there are some problems where you can't really do it anyway other than using Lagrange multipliers. Whereas this problem totally lends itself to either isolating a variable and writing it as a function of 2 variables, or also using Lagrange multipliers. But Lagrange multipliers often make the math easier. So let's take a look at this problem again, but through the lens of Lagrange multipliers. So again, with Lagrange. So with Lagrange, and the way you're doing it in your class is typical. We're going to say the thing you want to maximize is little f of x. So little f of xyz in this case. So f of xyz is the thing you want to optimize, which is your xy plus 2xz plus 2yz. And your constraint is what we're going to call g. And I think the way your professor is doing it is he's setting the constraint equal to 0. Yeah, which is typical. As long as it's equal to a constant, it's actually going to work out fine. But it's totally good to say our constraint, which is g of x, y, z, is the thing we want to, which is our setting our volume equal to 32. So we're going to say it's x, y, z minus 32. I guess it's true that it's equal to 0. Although I don't think we really need to write that down. Okay, so now we're going to find capital F of x, comma y, comma z, comma lambda, which is just going to be little f minus lambda times little g. So it's going to be our xy plus 2xz plus 2yz minus lambda times xyz minus 32. I don't recommend multiplying this lambda through. And I don't think he did either in class. So all we're going to do is we're going to take the partials with respect to each variable. So fx is going to be the partial of this with respect to x. So it's y plus a 2z. And minus a lambda times yz. And fy is going to be, partial with respect to y is going to be an x plus a 2z minus a lambda times a, let's see, xz here. And then fz is going to be, let's see, 2x plus a 2y minus lambda times xy. And all of these we're setting equal to 0. That's what we do with our partial. And you could write down f lambda, and you really don't need to, because all f lambda is your constraint again. So if I write down f lambda here, it feels kind of silly. The partial with respect to lambda is the derivative of this, so it's going to be -1 times xyz minus 32 equal to 0. If I multiply both sides by -1, I'm just back to my constraint. So I don't typically like to write down f lambda because it just feels like a waste of time, but you can, it's totally fine. This is where things get interesting. When you're trying to solve this system here, there's kind of a lot of ways to go. Most people start off with, although it's not always the right way to go, but most people start off with isolating lambda in each of these equations. It's not always 100% of the time the right thing to do, but it's usually the place to start. So if I'm going to do that here, I'm going to say, okay, well, y plus 2z equals lambda times yz, and then I'm going to divide both sides by yz. So y plus 2z divided by yz equals lambda. Same deal here. I'm going to have x plus 2z divided by xz equal to lambda. And same deal here. I'm going to have 2x plus 2y divided by xy equal to lambda. Usually the way that, so this may or may not feel, like this might not have been the best example. This might not feel easier. That's fine. It's still good to look at. Usually the way we then solve this is by picking two of the lambdas to set equal to each other and solving for what we can. So if I set these two equal to each other, I'm going to have x plus 2z over xz equal to y plus 2z over yz. This doesn't look great. I'm not going to lie. I would probably multiply both sides by z to get, so I can really just cancel those z's. And now I've got x plus 2z over x equals y plus 2z over y. Divide each thing. So x divided by x is 1. 2z over x. Y divided by y is 1. 2z over y. Cancel the ones. And then I can divide both sides by z. Basically, I think at this point, you can probably see that x has to equal y for this to be true. Right? If 2z over x equals 2z over y, we're going to get x equal to y. Which shouldn't be surprising considering that we found in the last problem that x and y were the same. So then we do the same sort of thing with any other two lambdas. So we don't want to pick these two again, but we can pick like this one and this one. So then we're going to pick like these two here and do the same sort of thing. Here's what we're going for. We want to be able to essentially write x in terms of y and z in terms of y, or y in terms of x and z in terms of x. Basically, you want to be able to write two of the other variables in terms of the third variable, so then you can plug those all back into your constraint and solve for whichever one variable is in there. So I'm going to look at these. I'm going to say, okay, x plus 2z over xz equals 2x plus 2y over xy. I'm going to cancel the x's. I guess I'm going to, divide by, so I'm going to get x over z plus 2z over z is 2 equal to 2x over y plus 2y over y is 2. The 2's cancel. And then I can cross multiply, maybe, sure. Yx equals 2xz, cancel an x, y equals 2z. Now, since I have equations that both have y's in them, I want to write each thing as in terms of y, meaning I actually want to go one more step here and say y divided by 2 equals z. So then I can plug in y over 2 for z and y for x. And so if I go back to my constraint now, I have that x times y times z equal to 32. I'm going to plug in y for x and y over 2 for z. Multiply both sides by 2 and say that y cubed equals 64, or y is equal to the cube root of 64, which is 4. And then you can plug back in over here and say, oh, z is 4 over 2. And x is also 4. So it works, and it definitely produces the same result. Now, one of the downsides about LaGrange multipliers is it doesn't actually tell you if the thing is a maximum or minimum. So you kind of have to use context to see if it would be a maximum or minimum. Here, I don't know, one thing I like to think about doing, but don't actually really do, is think about plugging in other values for x, y, and z that would work. So for example, a more extreme value would be if x was 32 and y was 1 and z was 1. That shape would have the same volume. And if you calculate the surface area for that, it's going to be a lot more than the surface area we get if these are our values. So it's not something like people talk about how you would have to check to see if the maximum in some other kind of way, but rarely people actually do that. So, questions so far? Okay. Let's look at a few more examples, because there are some examples that really lend themselves to LaGrange multipliers better than other things. For example, let's find the point on the surface z squared equal to xy plus 4 that is closest to the origin. So without saying it, they've asked us to do something. They've asked us to minimize the distance between a point on the surface and the origin. So if I draw some pretend surface, that's going to look kind of weird. Let's just pretend this is my surface here. I want to find the point on this surface that is closest to the origin. In other words, I want to minimize the distance between the origin 0, 0, 0 and my point that I don't know, x, y, z. Fun, actually not so much, well, fun, but more importantly, useful fact. Instead of minimizing the distance between two things, which in this case will be the square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared. That looks terrible, sorry. It is always as effective to minimize the square of the distance. So instead, I'm going to minimize the square of the distance, which is just going to be x squared plus y squared plus z squared. Totally works all the time. Because, and here's the way you want to think about it if you're not sure about this. If I'm trying to minimize the distance, I'm trying to make the inside of the square root as small as possible, which is literally what I've written down here. The inside of the square root, I'm going to make that as small as possible. And let's use LaGrange multipliers. So, trying to minimize this. This is our constraint. So my function f is x squared plus y squared plus z squared. My function little g, I'm going to bring everything to the left. Sure, why not? So g of x, y, z is z squared minus xy minus 4. And then finally, my capital F of x comma y comma z comma lambda is x squared plus y squared plus z squared minus lambda times z squared minus xy minus 4. Okay. And then it's the same thing over and over and over again. So we find all of our partials. Now, here's something I want to mention just because it's how it's presented in other classes. But all you're really doing here is you're setting the partials of the thing you want to optimize equal to the same partials times a constant of the thing that's your constraint. So some people, you might see this, you probably don't see. Some people might say you're just setting fx equal to, or little fx equal to lambda times little gx, and little fy equal to lambda times little gy, and so on and so forth. But this is a perfectly fine way of thinking about it. So here my fx is going to be 2x minus lambda times the derivative of this inside part with respect to x is negative y. And then my fy is going to be 2y minus lambda times negative x. And then my fz is going to be 2z minus lambda times the derivative of this with respect to z is 2z. Oh, interesting. Sure, yeah. Yeah, okay. So usually things are weird with Lagrange. I'm not gonna lie. Like it always feels like kind of a guessing game because you're trying to solve each of these equal to 0. And I will point out technically here, z equal to 0 would be a solution to this partial equaling 0. But z equal to 0 is not a point on the surface. If z is 0, oh, could it be a point on the surface? I might be a giant liar. Z could be 0, right? X could be like -2 and y could be +2. That would work. Okay, I totally lied. Z could be 0. it's probably not going to be 0, but you never know. So sometimes you don't want to, what I'm trying to say in the longest way possible here, feels like, you don't always want to go directly to solving for lambda. Because if I say, 2x equals negative lambda times y, and then lambda is negative 2x over y. Oops, lambda. It just sometimes leaves out possibilities. Right here, yeah, that's fine. Same deal here. 2y equals negative lambda x. So you get 2y over x negative equal to lambda. And then here, if I did the same thing, I would have 2z equal to 2 lambda z. And if I divide by 2z, I get lambda equal to 1. Which is true, but I should say I also could have gotten z equal to 0. So what I probably should have done here, instead of explicitly solving for lambda, is factored out a 2z. And said 2z times 1 minus lambda equals 0. So that you actually get z equal to 0, or you get lambda equal to 1. Okay. Yeah, I'm kind of curious how this is going to go. We're going to find out. So using lambda equal to 1, we can say, okay, well, if lambda equals 1, then negative 2x over y equals 1, and negative 2y over x equals 1. Is that going to work? It might not work, right? It's totally possible that lambda equal to 1 is not going to work out here. It feels like it's not, because if that's going to be true, oh, well, no, there's one way it could be true, I guess. Yeah, it's going to be interesting. So if I do this here, I get y equal to negative 2x, and I get x equal to negative 2y. If I plug in that there, I get y equal to 4 times y, which means y has to be not 1, 0, right? You can subtract 4y or subtract y, and then you get 3y equal to 0. And here, so x, right, and then if y is 0, x is also 0. So then if x is 0 and y is 0, no solution, right? Because, oh no, that's totally, my brain sometimes is like, no, this doesn't want to work. If x is 0 and y is 0, then looking back at our constraint would be z squared equal to 0 plus 4, which means z is either plus or minus 2. So here are some potential winners: 0, 0, 2, or 0, 0, negative 2. Okay. And either one of those would actually give you the same distance value, right? The distance between 0, 0, negative 2 and 0, 0. I mean, right, both of these are just 2 away from the origin. I think we can see that. The other option, though, would be if z was equal to 0. So if z is equal to 0, then lambda can kind of be anything. So let's go back over to, I always like run out of, there's not quite enough room on the page. Maybe I can make this fit. So if z is equal to 0, then we've still got these two equations, but now we're just going to set these equal to each other. So then we've got negative 2x over y equal to negative 2y over x. Multiply both sides by, or cross multiply, and divide by negative 2, we get x squared equal to y squared. So basically x and y are equal to not the same thing. If x squared equals y squared, you essentially get absolute value of x equal to the absolute value of y. Great. So let's plug that back in and see what we get. Yeah, I don't remember. So back into our constraint. Our constraint is, I feel like this, well, we're gonna do some exploring here. So our constraint is going to be, sorry, you can't see that. Z squared equal to either, you can say x times x plus 4, right? Because I'm saying x could be equal to y, or z squared equals x times negative x plus 4. Oh, but you know what I forgot to do? I forgot to plug in z equals 0, because that was also one of the conditions here. So really I should have 0 equal to x squared plus 4. That's not going to work. Or 0 equal to negative x squared plus 4. That will work. How weird. So if x is plus or minus 2, then y could be, well, if x is 2, y is going to have to be -2. If I'm looking at solving 0 equal to xy plus 4. Or if x is -2, y is equal to 2. This problem is funky. Like, I feel like this one's a little kind of extra. So here are other possible critical points. 2, -2, 0, and -2, 2, 0. Okay. So which of these is the closest to the origin? 0, 0, 2, 0, 0, -2, or these guys? Well, which one has the smaller distance value? I think it has to be. Sorry, I know I've covered them up. I think it has to be these guys here, right? Because I mean, right, 0 squared plus 0 squared plus 2 squared is 4, and 2 squared plus -2 squared plus 0 squared is 8. So these are the points that are closest. Kind of weird, right? So maybe it feels like we did more work than we should have, possibly, but I don't think so. Sorry, I feel like this example is it's okay. The reason I picked it though is because I feel like I saw a homework problem that was similar to it. I guess not. I guess I'm a liar. There was a homework problem similar to this, but they just did it the other way. Like, so there are on your homework assignment, there's a couple problems, I think, like 2 literally, that say you do this using LaGrange, and then the rest of them are just optimization kind of the other way. So I suppose it's worth noting here that maybe LaGrange was the, I don't want to say wrong way to go, just the more challenging way to go. If we had done this the other way, it's actually not too terrible, I think. So just looking at it the other way, if we're trying to minimize this distance squared, then, and we have the constraint that z squared equals xy plus 4, I guess it's pretty easy to plug that in here. So we could say we're minimizing this function of x and y, which is x squared plus y squared plus z squared. And I guess this would be easier. Sorry, I did it the hard way first. So fx would be 2x plus y. Fy would be 2y plus x. And setting this equal to 0, yeah, I feel like it's interesting though, because I feel like we miss out on possible other critical points. So here we get y equal to -2x. Here we get x equal to -2y. And if you plug those back into each other, you're getting x and y equal to 0. And that's the only solution to this, which ended up being our critical point, right? Or I should say critical points. So here we would see, oh, yep, our points are going to be 0, 0, and z has to be 2 or -2. And these are both answers. Both of these points minimize the distance to the origin. Interesting. Okay. Let's look at the better problem. You guys are like, yes, please. Let's look at, I had one somewhere around here. Yeah, okay. Let's say this problem, I would say this problem is similar-ish to your problem 10 in your homework, but not exactly the same. So let's say we want to find both the maximum and minimum value of the following: f of x comma y equal to 3x plus 4y on x squared plus y squared equal to 1. And I certainly, well, I know the instructions are to use LaGrange, so I'm not even going to think about doing it the other way, because I feel like doing it the other way gets a little weird. If you solve for y and plug that in, it's just, I don't know. I mean, right, taking the partials isn't helpful here. Fx is 3, Fy is 4. That doesn't lead to any critical points. So sometimes you have functions that don't have critical points on their own without the constraint as kind of a other piece of information. So let's see what happens using Lagrange. So there's my f, and I guess I should say that my g is x squared plus y squared minus 1. So my capital F of x, y, lambda is 3x plus 4y minus lambda times x squared plus y squared minus 1. That's fine. Cool. So taking the partial with respect to x, we get 3 minus 2 lambda x, saying that equal to 0. Taking the partial with respect to y, we get 4 minus 2 lambda y. 0. I actually want to see one thing here. All right, one moment. I'm going to check one. Grab this example from somewhere in there. I feel like there was something weird with the solution that I just wanted to check on, but I'm not finding it. Oh, I know. That's because this problem is from over there. Sure. Okay. Totally fine. All right. I guess I'm solving for lambda. So I'm going to say that 3 equals 2 lambda x, so that 3 over 2x equals lambda. And then 4 equals 2 lambda y. So 4 over 2 lambda equals, sorry, 4 over 2 y equals lambda. I should say 2 over y equals lambda. And then we set those equal to each other. So then it's going to give me 3 over 2x equal to 2 over y. Do some cross multiplying. 3y equals 4x. Pick your poison. I typically would probably solve for y in terms of x. So y is going to be equal to 4/3 x. Okay. So then we plug that into the constraint. Again, just to reiterate, you don't need to write down f lambda, right? You totally can. It's totally fine. If you want to do it, you should do it. But we know that f lambda is just the constraint. So I'm taking this and plugging it back into the constraint, and I'm going to get x squared plus 4/3 x quantity squared equal to 1. And then simplifying this, I've got x squared plus 16 over 9 x squared equal to 1. Combine those together, that's a 9 over 9 x squared. So I've really got 25 over 9 x squared equal to 1, which is going to give me x squared equal to 9/25. So x is going to be plus or minus the square root of 9 over 25, which is 3 over 5. Oh, sorry, you can't see that. And then if we find the corresponding y values, so if x is positive 3/5, y is going to be positive 4/5. So one of our critical points is 3/5, 4/5. And the other one is negative 3/5, negative 4/5. Right, because I'm just multiplying the 3/5 times the 4/3 to get the 4/5. And then one of those is going to maximize this thing and one of them is going to minimize it. And we can just check. If we plug in 3/5, 4/5, that's going to equal, well, 3 times 3/5 plus 4 times 4/5 is going to be 25/5, which is 5. And that would be the answer to what is the maximum value. So something else to look out for with these questions is sometimes they'll ask you for the coordinates or the dimensions that maximize the thing. And sometimes they'll ask you for the output that is the maximum value. Just make sure you're paying, especially on web work, right? Make sure you're paying attention to what they're actually asking for. So that's going to be our maximum value. Well, I think it is. Let's check the other one. If I plug in negative 3/5 and negative 4/5, I'm going to get negative 9/5 minus 16/5, which is negative 25/5, which is negative 5. So this is the maximum value. And that's the minimum value. It's kind of worth thinking about other values you could get just for a second. So on this circle, there's a couple of easy points I could plug in. Like if I plugged in 1 for x and 0 for y, I get 3 plus 0, which is 3, which is not the biggest, right? Or if I plugged in 0 for x and 1 for y, 0 plus 4 would be 4. So again, right, there's a couple other points that are not giving me the maximum value. So not that that's a proof of any sort, but it helps me kind of know, oh yeah, that seems reasonable, right? Like some other points are not just magically giving me a higher or a lower low. So it seems all right. Yeah. Let's see. I think I had one other one that I wanted to do, and then yeah, that should be fine. Let's look at. Sure. Yeah, okay. This one, I see. Here's the one. Here's the one that had the thing that I think is kind of interesting. Yeah. Again, I will just kind of say with LaGrange, it's all about the setup. And then figuring out how to solve for x, y, lambda, whatever. And I should say that it's kind of, how do I say it the right way? It's not algorithmic. There isn't always one right way to go about trying to solve a system of LaGrange multipliers. Most of the time, problems I see, usually it comes down to solving for lambda and then setting things equal to each other and getting x and y in terms of each other or whatever, but not always. So there's no like tried and true method that always is going to work for LaGrange, or at least always is going to work easily. Let's look at a similar problem to the one we just did. Let's say we want to find the maximum and minimum values of f of x, y equal to 3x squared plus y on the same circle. So it's kind of weird, like, so the way I'm kind of thinking about this is like, here you've got some function of x and y, it's some surface in three-dimensional space. And what you're kind of saying is, okay, if you took that, in fact, why am I trying to, I could actually, there's actually ways to graph this. I could just, like try to show you for real instead of like trying to wave around with my arms. So let's look for a second here. Let's make this big. Where's the thing I want? Sorry, one second. Okay, so my first function there was z, or f of x, y, which I'm thinking of as my z, equal to 3x squared plus y. Okay, it looks kind of funky, but not too funky. You can kind of see that there. Okay. And then what we're going to do is we're going to see, well, okay, but specifically on this circle, sorry, on this cylinder really is what it actually is. Why'd you change colors? I don't want you to be red too. That's lame. Anything but that. Okay, great, awesome. So what we're kind of looking for is where. So it looks like to me, down there is probably where the minimum value is. Right? That's kind of the lowest point on this red surface that is cut by this blue cylinder. And it looks like my highest points are going to be here and here. So it's kind of funky, right? You've kind of got this, like, right, this thing that's kind of going up and down and up and down. So it kind of, if I could maybe attempt to draw it, I like when it does that. Kind of fun. We've got a kind of a surface that looks like this. I know you can't see what I'm drawing yet because it's probably going to be terrible, but whatever. Sorry, my drawing skills are. That's all right. So, yeah, okay, we're done with you. So we're kind of looking at like something like this, where this is the bottom, the minimum, and these are the tops. And this point down here, right here, that's a local minimum, but it's not like an absolute maximum or absolute minimum. We're kind of asking about the absolute. I know I didn't say that, but I should have. So kind of cool to see like what's actually going on. Right? I feel like that graph is helpful. So let's do the thing. So again, LaGrange. I feel like I need a whole new piece of paper because I just made that one look terrible. Let's write this again real quick. Find the absolute maximum and minimum value of f of x, y equal to 3x squared plus y on circle, cylinder, x squared plus y squared equals 1. All right, so same deal. We're going to Lagrange it up. F of x comma y comma lambda is equal to 3x squared plus y minus lambda times x squared plus y squared minus 1. I do want to point out, just because I think you probably noticed by now, right? The minus 1 here is inconsequential, right? You don't need this constant here actually, because the partial derivatives don't care what that's doing, except for the part, unless you're also writing down the partial with respect to lambda, but that's just your constraint. So again, it's really unnecessary. Partials. Fx is going to be 6x minus 2xy, 2x lambda, holy smokes. Fy is going to be 1 minus 2y lambda. And here's where things get a little bit weird, I think. This one right here, normally I would do the thing where I solve for lambda, but I shouldn't, because solving for lambda here is actually going to limit my options. If I solve for lambda, let's see what would happen. I would get 6x equal to 2x lambda, and then dividing both sides by 2x, I get lambda equal to 3. And not that that isn't correct, it's just not as correct as it could be. Because what I could actually do here and should do here is factor out a 2x. I should say 2x times 3 minus lambda equals 0. So what I've really actually got is either x equals 0 or lambda equals 3. Okay, and then for fy equal 1 minus 2y lambda, we can just kind of do the thing where we say, sure, 1 equals 2y lambda, and lambda equals 1 over 2y. Or maybe even 1 over 2 lambda equals y. The reason I'm writing both of these here is because I know I've already kind of got conditions. So if I, for example, say I'm going to look at lambda equals 3 first, well, then finding y is super straightforward. If lambda equals 3, then y is going to equal 1 over 2 times lambda. And then I can go back to my constraint to figure out what x has to be. So then x squared is going to equal 1 minus 1/6 squared. So x is going to equal plus or minus the square root of 1 minus 1 over 36, which is 36 minus 1 all over 36. So 35 over 36. Terrible. Not my favorite number ever. So here's a couple critical points. We've got plus or minus square root of 35 over 36, comma 1/6. But then we also have x could just be 0, right? And if x is 0, I can toss that into my constraint and say, oh, well, if x equals 0, then y squared equals 1. So y equals plus or minus 1. So here's my other 2 critical points. Okay, so let's plug them into the function, because the only way to see which one's the biggest is to literally see which one's the biggest. So f of 0, never enough room. Never enough room. Okay, so what's f of 0, 1? F of 0, negative 1. And then plugging in these points, which is a little bit less nice. But so I'm going to do these both at once, because I can see that when it doesn't matter if x is positive or negative, when I square it, it's going to be positive. So f of either positive or negative square root of 35 over 36, comma 1/6 is going to be, let's see, so I'm going to get 3 times 35 over 36 plus 1/6. Those cancel and give me a 35 over 12 plus a 2 over 12, which is 37 over 12. Okay, so of these 3 numbers, which one is the smallest? Which one's the largest? Right. So our absolute maximum value is 37 over 12. And our absolute minimum value is negative 1. Kind of weird. Kind of interesting, but kind of weird. So I imagine you're not going to see super complicated LaGrange examples, right? Like there's a couple on your homework. It might not even come up on an exam because it's usually just, it's not really a great exam type question usually. I don't know, the amount of problems on your homework makes me think you're probably not going to see a whole lot of it. So time is it? 10:47. So looking forward, unless there's a question you specifically want to ask about Lagrange multipliers. I think there are, okay. Next time we'll talk about double integrals. And I'll just point out one thing for now. So let's say I wanted to use a double integral to find an area. So I want to find the area of the region bounded by, let's make it not too terrible, James, y equal to 9 minus x squared and y equal to 0, which looks like this. Usual parabola, opening downwards, got some points there, some points there. One way to do this using just a single integral would be, well, I'm just thinking of this is like the height of my rectangle. So the area of that rectangle is just my little dx times the height, which is the function. So the area of my rectangle is 9 minus x squared times dx. And then I add up all the rectangles. So my area of my rectangle. So that doesn't say area, by the way. That says a sub rec. That's what I actually wrote there. I wasn't trying to write area. It looks kind of like area when I look at it. So my total area, I'm just adding up all the rectangles from x equals -3 to +3 of 9 minus x squared dx. Or another way you can do this is by using a double integral, which you normally wouldn't, but there's reasons why we kind of start off this way. You could say the area is going to be, well, first I'm going to talk about what y is doing. So y is going from 0 to 9 minus x squared. That's my lower bound, my upper bound for y. And then my outer integral is going still the same thing from x equals 0. So 0, not 0, from x equals -3 to x equals +3. So when I look at this, I see the inner integral, which you deal with first, and then the outer integral, which you deal with second. Now, people usually don't write x equals and y equals. I mean, people often do, but it's not strictly required. So you would normally see this written more as the integral from -3 to 3 of the integral from 0 to 9 minus x squared of 1 dy dx. Sometimes people don't even write the 1 because it's kind of implied that it's there if you don't write it. You have to have something times dy. There's always a 1 times dy. So the way you would do this integral is by first integrating 1 with respect to y. So just like a partial derivative, you differentiate with respect to the variable and you treat other things like a constant. When you anti-differentiate with respect to one variable, same kind of deal. Any x would be treated like a constant. There aren't any right now, but here's what I mean. So if we integrate this, we get the integral from -3 to 3. And then this inner integral, well, what's the antiderivative of 1? Right, exactly. Why? Because we're anti-differentiating with respect to y. And then we're evaluating that from 0 to 9 minus x squared. And then we plug those limits of integration into every y that we see. So you end up getting the integral from -3 to 3 of 9 minus x squared minus 0, if you like, dx, which is literally the same as that. Which we could then do. Like, the point is not to do the integral fully. The point is to see that this process here of double integration yields the same result as this process of single integration. What we're going to move on to is saying, well, much like you can integrate a single integral, like you can integrate a function to find the area under that function, you can integrate a function of 2 variables over some region to find the volume under that surface. That's going to be what we're kind of going to be doing. It's going to say, instead of just integrating 1 and getting the area, we're going to integrate some actual function of x and y here and get a volume. That's kind of it. I mean, that's not it, but like, that's it for now. We'll talk more about it on Wednesday. Yeah, the thing I would say to keep in mind is that when you're doing integration, like if this were a function of X and Y, all the Y's would be treated like variables and you would actually like do, power rule or whatever to them, and all the X's would be treated like constants. So they would just hang out. Or if you had like an X on its own, its antiderivative would be X times Y because, right, we're anti-differentiating, not differentiating. Okay. That's all I have to say for real.